Alright, so what we're going to do is we're going to look at some of the more complicated examples that come up and some patterns that come out of them. And we're also going to look at when factors are prime. And so what I'm going to do is I'm going to go through most of the evens in 61 through 92 and just point out some things. So we'll start with 62, which is a squared plus 5a plus 6. So we look at C, all right, and it's a positive 6. So our factors of C are 1, 6, 2, 3, negative 3, negative 2, negative 6, negative 1. We add these up, we get 7, 5, negative 5, and 7. Well, our B term is positive 5, so we want these. And so we get A plus 2, A plus 3. So it works out nicely, right? Use our methodology there, and we're doing pretty good. All right. Let's go down a bit, and let's look at 64. 64 gives us A x plus B plus bx plus A. What we want to do, I think, is kind of group terms together. So I'm going to put everything that has an A up front. I'm going to put everything that has a B out back. And then I'll factor by grouping. And so I arrange terms together, and so I'll pull the A out front, and here I'll pull the B out front. And this shows a little trick about factoring by grouping, that you have to get the terms together that match. This doesn't really pose a problem with one variable. But once we start having more than one variable, you're going to want to group things together. And so I grouped the A's together, and I grouped the B's together, so that they would pull out and leave behind this x plus 1 term. So with one variable, you don't have to worry about this as much because your grouping will happen relatively naturally. But with two variables or more, you should start worrying about keeping your groups together. And you'll see this as we go through different problems. All right, so 64. Let's look at 66. X squared plus 49. All right, I've got squares, but it's not a difference. All right, well, I can use this. Nope, that's sum of cubes, difference of cubes, special product. This is prime. There is no pattern that will make this easier. And there's no common term I can pull out. For the difference of squares to work, this has to be a negative sign in the middle. And there's nothing we can do to this. And so this is an example of what prime looks like. All right, now let's look at number 68. 1/16 minus b squared. All right, well, we have a difference, so it would be nice if these were squared. So if a squared equals 1/16, then a equals, well, the square root of 16 is 4. The square root of 1 is 1, so that's 1/4. And if b squared equals b squared, then b equals b. It's funny when variables match the pattern we're looking at. Well, now we can take our pattern for difference of squares, 1/16 plus b, or whoops, not 16th, 1/4 plus b. Got to catch yourself sometimes. And 1/4 minus b. Okay. Let's look 70. I'll let you play with 70 if you want, but I want to look for some more complexities in these, so I'm going to jump down to 90. X to the fourth minus 1. So I'm going to say this is a difference, and I know 1 is a square. So I'll say a squared equals x to the fourth. So a equals x squared. And b squared equals 1. So b equals 1. So this means my difference of squares gives me x squared plus 1 and x squared minus 1. But I'm not done. Actually, look at this again. This is another difference of squares. And so my first term doesn't break into any more factors, but this next term is x plus 1, x minus 1. And it loops down in a pattern. And this can happen sometimes. There will be loops where you resolve a difference of squares and you get a difference of squares, or you resolve a cube and you get cubes underneath it all. Let's look at 86. So for 86, I have x to the sixth minus 7x cubed minus 8. There's a pattern we should notice here, and sometimes we can do what's called U substitution to take care of this, or we can look for the pattern. But notice how x to the sixth, x to the third, well, we're used to seeing x squared and x. Well, can I make this look like that? So I'm going to do a little trick here called U substitution. I'm going to say that U equals x cubed. Well, what would that make U squared equals? Well, U squared would be x cubed squared, which equals x to the sixth. So this is U squared minus 7U minus 8. Alright, so that's good. What I can do is then factor this. So my C is negative 1 times 8, negative 2 times 4, negative 4 times 2, and negative 8 times 1. When I add them up, this gives me 7, this gives me 2, this gives me negative 2, this gives me negative 7. This is the answer I want. So I'll rewrite my factors as U minus 8 and U plus 1. But U was x cubed. So I get x cubed minus 8 and x cubed plus 1. I have cubes. So the first thing I'm going to do is I'm going to check to see if these are in my cubes. And I do. 8 is cubed and 1 is a cube. So I have a difference of cubes and a sum of cubes in this one. So my next step here is I'm going to expand those out. So I get x minus 2 times x squared minus plus 2x plus 4. And so that was this first term here. It gives me these. Now I want to look at my second term here. Get x plus 1 times x squared minus x plus 1. All right. And at this point, we're done. there's no factors of 4 that add up to 2. Right? Well, 1 and 4, 2 and 2. Oops, scroll down here. -1, -4, -2, -2. This adds up to 5. This adds up to +4. This adds up to -5, -4. So none of these add up to 2. And the same here. There's no factors of 1 that add up to -1. I have 1 and 1, -1, and -1. If this were a -2, it'd be good, but it's not. So these are our factors from this. X to the 4th minus 1. And I'll leave it to you as a test that if you go back and remultiply all of these, well, it's not x to the 4th minus 1, x to the 6th minus 7x cubed minus 8. Sorry, I scrolled up to yellow. I was trying to color code things. But these are the factors to x to the 6th minus 7x cubed minus 8. Sorry about that. But if you multiply these back through, you will get this. And these are probably the more complex examples you see. This is a test type question. On the hardest part to see if you can work your way through everything. You probably won't see it as much in this unit as you'll see it then when we actually start solving equations that use these. But it's a good habit to realize that any technique we do here in and of itself is not always the ending step. We're going to be manipulating these expressions and quantities to get something from it. And sometimes we have to do the manipulations over and over again until we